Okay, so what I've decided is to do lecture 5 while I'm sitting here. So lecture 5. So lecture 5 is going to cover another trick, as well as substitution, called by parts, and also sort of more, I wouldn't stretch to say completely, but more practical application of integration, called the volumes of revolution. So let's have a look at by parts first of all. So integration by parts is a trick that essentially takes the product rule that we looked at previously, uses it in reverse in order to make impossible integrals possible. Not easy necessarily, but possible. So if we look at the product rule, I'm going to write it in a slightly different way than we wrote it before. So we've got d by dx of f times g. Remember, two functions, f times g, so f is equal to f of x, g is equal to g of x. We said that was equal to, and I'm going to mix my notation up a wee bit here. F dash g plus f g dash. If we then integrate through here, integrate everything, so by x, then that should undo this. So this tells us that fg is going to be equal to the integral of f dash g dx plus the integral of f g dash dx, or another way to put it is that I'm going to make this the subject, and you'll see why in a second. F g dash is equal to, move that across, fg minus the integral of f dash g dx. So on the face of things, all this thing's saying is that if we can take one of the integrals, we can take this integral, an integral that's made up of the multiplication of two parts, then we can restate it as this combination of a part that we don't have to integrate, I've wasted that, and a part that we still have to integrate. Which, if we pick which part we're going to, so we're changing things around here, but essentially if we start with this, we're differentiating f to get f dash and integrating g dash to get g. If we pick those cleverly, then it can transform an integral to something we just don't have a rule to do, and it's something we do have a rule to do. I'm going to change the notation slightly. Going to use u and v instead. The integral of u v dash dx is equal to uv minus the integral of u dash v dx. Or for definite integrals, for doing it between a and b, of u v dash dx is going to be equal to uv evaluated and subtracted at points a and b minus the definite integral of u dash v dx. So these are our two cases where we've got definite integrals versus indefinite integrals. So our whole game here then is to hope that we can actually take this hard integral and hope that this second integral here is an easy integral. And picking what represents u and what represents v in such a way that this integral is easy is possible to be completed. So let's look at what kind of things we are talking about here, and a sort of the way we should lay this thing out. So let's say someone said, find me the integral of x sine x dx. Now the paper will tell you to use integration by parts, but it won't tell you how to do it. You'll have to to see which one is u and which one's v. So I'm going to set out a wee table here. Table, not really a table at all, but just 4 things. And we're looking at this thing and saying, well, if the integration by parts rule says that uv dash becomes uv minus u dash v, and we want this to be easier, then what ones these are which one of these two is going to become easier when we either integrate or differentiate it? In general, things don't get easier when you integrate them. Very rarely is that going to happen. So we're really looking at the question, which one of these gets easier when we differentiate it? Of course, sin x, when we differentiate it, becomes cos x, which when we differentiate it again becomes sin x, minus sin x rather. So arguably it stays as complicated all the time. But x becomes 1 when we differentiate it. So I would suggest we make u x. And now this forces us to make the other thing v dash. So if u is x, then sin x must be v dash. So we've picked u is the thing we're going to differentiate, and pick that such as the thing that becomes simpler once we differentiate it. So u dash is what we get when we differentiate this thing. X becomes 1 when we differentiate it. And sin x becomes, so we're going to integrate to go from v dash to v, so it becomes minus cos x. So following this rule, we're going to reinsert this thing. So if this was that, then it transforms into u times v, so x times minus cos x minus the integral of, and then this says u dash v, so 1 times minus cos x. Now the key bit here to recognise is that this bit doesn't need integrated anymore, this bit's done. So this becomes minus x cos x minus the integral of minus cos x dx, so 1 times minus cos x minus cos x. We make that a bit simpler for us well, minus x cos x minus minus is a positive, plus the integral of cos x dx. So this becomes minus, cos x plus cos x integrated becomes positive sin x plus z. So this thing we should recognise that we can integrate this straight away because it's a product of two functions. But in this particular case, it allowed us to take a product of two functions and treat it as if it was a product of still two complicated functions minus the integral of a simpler function. So minus cos x, or cos x itself, is something we can definitely integrate. But x sin x isn't. I'm going to change pens. I've decided, I've made an executive's decision that although I like the broad ink of that pen, it's getting a bit too smudgy. Maybe I'm just getting a bit too touchy-feely with my own stuff. Let's do the definite integral. 0 and 1, I like 0 and 1 because 0 and 1 do nice things to our functions, of 5x times 2x plus 8 to the 7 dx. Now remember, going to put a rule down again here. u v dash integrated gives you uv minus the integral of u dash v dx, but we're going to put limits in as well, so let's fix that a little bit. 0, 1, 2, 0, 1, 0, 1. So u is the thing we want to differentiate. and v dash is the thing that we want to integrate. So the thing we probably want to differentiate here is 5x, because it's going to disappear. Or it's not going to disappear, but it's going to become a lot simpler. It's going to become just 5. We differentiate it. Forces us to think that 2x plus 8 to the 7 is a v dash. And when we integrate that, we get 2x plus 8 to the 8 over 16. In other words, this 8 times this 2. Revise, go over your higher if you want to remember how that is, if you're confused by why it should be that. But essentially we're taking the factor in front of the x to divide by it and doing the add 1 to the power divide by the power thing. Anyway, so that's what our u dash, v dash and v are. So let's put these into this shape. So our integral of 0 to 1 of 5x 2x plus 8 to the 7 is going to be equal to, so uv, so it's going to be this thing here, 5x times 2x plus 8 to the 8, and let's put the whole thing over 16 between 0 and 1, minus the integral of u dash v, so 5 times 2x plus 8 to the 8 all over 16 dx. Let me tidy this up a little bit to make it better for me. So that's going to be, I'm going to take the constants at the front here, so 5 over 16 of x times 2x plus 8 to the 8 minus 5 over 16, oops, that should be 0 1 there, 0 1 there, 2x plus 8 to the 8 dx. So I can put some numbers in here, so that's going to be 5 over 16 times, oops, 0 1, 1 times 2 by 1 plus 8 to the 8. Oh, probably should have picked better numbers here, never mind. Minus 0 times 2 times 0 plus 8 to the 8, close the brackets, minus 5 over 16 times 2x plus 8 to the 9 over 9 between 0 and 1. Okay. So this is going to simplify, let's simplify down that bit first. So that's 5 over 16. If I put 0 in there, 0 times this bracket gives you 0. So this thing's run out of steam anyway. So that's gone. I just need to worry about this thing. 1 times everything is going to be that. 2 times 1 is 2, plus 8 is 10, 10 to the 8, 5 16s times, I'm just going to write 10 to the 8, minus 5 over 16 times, again if I put 1 in here, you're going to get 2 times 1 plus 8 is 10, so 10 to the 9 over 9, minus, if I put 0 in here, you get 8 to the 9 over 9. So that's equal to 5 over 16, taking out that factor, so it's going to be 10 to the 8 minus 10 to the 9 over 9 plus 8 to the 9 over 9. Now I'm just playing with numbers, doesn't really matter. So this becomes 5 taken at the power of a ninth. It's going to be 1 over 144. 2 times that by 9. Times 9 times 10 to the 8 minus 10 to the 9 plus 8 to the 9. And now I'm going to do something that I rarely do and bring out a calculator if I can find one. 9 times 10 to the 8 minus 1 times 10 to the 9 plus 8 to the 9 divided by 144 . And that's roughly equal to, I'd love to have a nice fraction to tell you guys, but it's roughly equal to 1188115.556. Oh, okay, so there's a lot of number stuff in here, but the key stuff was up here, where we looked at this function and we decided what do we differentiate and what do we integrate to give us this, not necessarily easy, but resolvable integral here. This line here. We can, for these kinds of functions, we could have an repeated application. So we're going to do one of these quickly. So I don't like doing it very much. And it's not very applicable, but we could do it. So let's say someone said, can you integrate x squared sine x instead of x sine x? Well, we'd say, well, that's going to be easy. That's going to be u is equal to x squared. V dash is equal to sine x. U dash is going to be 2x. And V is going to be minus cos x. So, I've just ran through that quite quickly here, but we're always looking for the thing that's most likely to disappear, at least get simpler when we differentiate it. If not disappear, get closer to disappearing when we differentiate it. But of course we put this stuff together. uv dash is equal to uv minus the integral of u dash v. And that means that the integral of x squared sine x is going to be equal to uv is going to be minus x squared cos x minus the integral of 2x times minus cos x. Again, let me neaten that up. So that's minus x squared cos x plus the integral of 2x cos x dx. This has not got simpler. It's almost as complicated as it was before, but there's nothing stopping us from just doing the product rule again. Product rule? No, sorry, doing integration by parts again. So this time we say, well, we want u is equal to 2x, so u dash is equal to 2, v dash is equal to cos x, which means that v is equal to sine x when we integrate it. So this x squared sine x is equal to minus x squared cos x plus, and I'm going to put in a bracket, this stuff here. This transformed using the integration by parts rule using this stuff here. So we get uv from here, this becomes uv, so 2x sine x minus the integral of u dash v, 2 times sine x. And that thing I can just integrate as well, so that becomes equal to minus x squared cos x, and I have reached the point where this is simple enough to integrate straight away, plus 2x sine x. Sine x becomes minus cos x, so minus 2 cos x plus c. Yep, and then just put that all together. Minus x squared cos x plus 2x sine x plus 2 cos x plus c. And that would be your answer right there. So we can repeatedly apply this until we get to where we're going. There's another rule here. I'm going to just a quick aside. This rule doesn't come in very useful except when we've got these repeated application questions where there's something we're going to have to, that's not simple enough to disappear right away, that we're going to have to repeatedly apply this. It's called the DE method, and the idea is that it takes into all the stuff going on here, all the differentiation, integration, and the plusing and the minusing, to get you to your answer quite quickly. So what we do is we write our two columns are going to be differentiate and DI method, sorry, I said DE, DI method, integrate, what you're going to integrate. So, and then we write plus, minus, blah blah, forever, doesn't really matter, but it alternates between plus or minus at the bottom. So we draw this table, plus, minus, and then the things we're going to differentiate, the things we're going to integrate. So we just, what one of these does it look like we're going to integrate, differentiate, sorry, x squared. What one's it look like we're going to integrate, sin x. And all we're going to do is differentiate each of these terms over and over again until one of them disappears. So x squared becomes 2x, 2x becomes 2, 2 becomes 0. Sin x becomes minus cos x, we integrate it. Minus cos x becomes minus sin x, when we integrate it. And minus sin x becomes positive cos x. And because this one's 0, we know that's the list we need to stop at. And then all we do, to put this together, to show this crossy overy thing that goes on here between you, and we start to look at the diagonals. And really we could have worked out one here, but we're going to be, each of these lines we're going to multiply. So if we were to do that line there, we'd be doing 0 times something, and obviously the integral is 0, 0, so this is where the thing would stop. So this tells us that for this question, is going to be that times that, the positive of that times that, so it's going to be minus x squared cos x plus the negative of this, which is going to be minus 2x minus sin x, so plus 2x sin x, because that minus and that minus cancel, plus that times that. And then in theory, plus the next line, but 0 times something would always get zeros after that, so plus c. So I've hit the same answer here with far less lines of working. Called the DI method. If you want to see it more in depth, look it up. There's tutorials online for it. But it just, if you had a function that was a much higher power, for example, this is quite good for speeding you through it rather than having to write this out in long form every time. Okay, last part, let's do integration to give you what we call the volume of revolution. Okay, so volumes of revolution. So imagine that we had a graph. and we had some function to describe. Let's keep this simple. Well, we had some function. If we were to then revolve that function through 360 degrees, in other words, going into the page and round, so round like that, if I can spell, revolve, you would get this shape, which would be a kind of a cone. I can't draw it all here. You get this cone by revolving this line through. So what the theory for volumes of revolution does is it tells us how to take this graph here and translate it into the volume of this shape you would get if you revolved it through 360 degrees. Now this is actually could be kind of useful if you want to work out how to make what volume a vase would hold, for example, just by knowing the profile of the side of it, like this. You could do so using this, and it was mathematically describable using the function. You could do so by using this method. So the idea is that all we're doing is we're saying, well, we're essentially adding up circles, or discs I should say. At each point here we're working out the volume of a little disc. Again, me being bad at drawing. That's what's going on here. And adding all these discs together through integration. So for each of these discs, so V disc is going to be equal to, well, our usual equation is pi r squared h for a disc, right? But if each of these discs is tiny, so the h is going to be in this direction, along this way. So h is going to be equal to dx, right? So a little change in x over the super thin disc. And our r is going to be equal to y, to the value y that we got here. So I've actually got values for both these things. So it's going to be pi y squared dx. So the width, h is the width of the disc, and y would be the radius of the disc. If we want to add all these things together, let's just say what integration is. Remember we've spoken before about integration takes a graph, cuts it up into little bits, and then adds them all up. That's all we're doing here. So volume of revolution is going to be equal to the integral of pi y squared dx, or to put it a slightly different way, pi times the integral, taking out this constant pi, between, if this is point A and this is point B, between A and B of y squared dx. That's our formula. We've got a function for y, then we square it, then we integrate it, we take it between the 2 points, we multiply our answer by pi, and that's us done. Now this is one of these interesting cases where actually the more complicated functions become the easier ones because of this squared thing here. This square could actually mess us up if we're not careful. So let's do a little example. Let's say we're doing a bowl that looks a bit like this. Or a lampshade or something like that. And let's say that this inner radius, or inner diameter I should say, is something like 2. This outer radius is something like uh, 4. So the profile, and this is 1. The profile of the above, I guess it's a lampshade, isn't it? We'll get round it. Above lampshade can be described by y is equal to 1 plus x squared. Find the volume of the shade between x equals 0 and x equals 1. So these numbers kind of make sense, because if x equals 0, then you get 1 plus 0 squared. So that would be from here to here is 1, so the diameter would be 2. And if x equals 1, then that would be 1 plus 1, which is 2. Here to here would be 2, so here to here would be 4. And then it's a step of 1. So this seems to fit this shape altogether quite well. So volume is going to be equal to pi times y squared between a and b dx. So that's going to be equal to pi times the integral between 0 and 1 on the function for y is 1 plus x squared dx. So we're going to have to do a wee bit of cosmetic work on this first before we want to integrate it. So that's going to be pi times the integral between 0 and 1 of, so we're squaring out this bracket, so that's going to be the first term squared is 1 plus the second term squared is x to the 4 plus 2 times the first times the second is 2x squared. You can multiply it out by yourself, but that's the general rule. First, if you're squaring a bracket of 2 terms, a squared plus b squared plus 2 times a times b. 1 squared plus x squared squared plus 2 times 1 squared times 2 times 1 times x squared. So let's integrate that. And I'm going to change the order as I do it. So x to the 4 is going to become x to the 5 over 5 plus 2x squared is going to become 2x cubed over 3 plus 1 is going to become just x between 0 and 1. Putting our numbers, so that should have a pi before this. So that's pi times, putting a 1 in here, it's going to be 1/5 plus 2/3 plus 1 minus 0, 0, 0. So that's pi times 3/15 plus 10/15 plus 15/15. 3 times 3, 5 times 5. So that's going to be 25, 28 over 50 pi. And that's your answer. Let's do another one. Find the volume of revolution of y is equal to root 1 minus x squared at 1 plus x squared between x is equal to 2 and x is equal to 5. So sort of more exotic numbers this time. So again we want the volume is equal to pi times y squared dx between a and b, which in our case is going to be pi between 2 and 5 of root 1 plus x squared dx, which simplifies greatly because we square a square root and we just get whatever was being square rooted, so it's going to be just 1 plus x squared dx between 2 and 5. So this becomes pi of that integrated is just x, that integrated is x cubed over 3 between 5 and 2. So that's pi of 5 plus 5 cubed over 3 minus 2 plus 2 cubed over 3. Let's put this together numerically. So that's going to be 5 minus 2 is 3 plus 125 minus 8 over all over 3. So that take away that, that take away that. So that's going to be 126 over 3. Pi. And that's your answer. Okay, so that was volumes of revolutions. Square your function, integrate the function between the limits, times your answer by pi. You can see I've not even bothered to give well, units first of all, but even give a decimal answer here. I've just left it in units of pi. Okay, so that's the integration lectures over. Not much integration in this actually, now that I look at it. But yeah, we're done. I'll talk to you again once I've done a couple of quizzes, and next we'll be doing differential equations. Okay, stay well, and I'll talk to you soon.